Okay, so continuing with our videos on techniques for solving problems in dynamics, we will solve a problem on finding the velocity of a point on a rigid body, and we will use the concept of rotating frames. So the problem that we are going to consider today in this video is that of a rolling cone. So assume that here is a cone that is rolling on a horizontal surface. Okay, now the cone is rolling without slipping, and its angular velocity of rolling is omega, as shown here. And the cone has the angle that the cone makes is 2 beta, so each of these angles is beta, and the radius of the cone is small r. Okay, and the question goes as follows. So this is rolling without slipping. So the question goes as follows, that at an arbitrary instant there is a point P on the circumference of the base circle, and let's say that with respect to the this diametrical line that we draw from the point of contact of this circle to the topmost point. So using that as a reference, the angle that the point P makes is phi at an instant. Okay, let me just bring this to a better focus. Okay, so hopefully now the picture is a little bit clearer. So let's say this point is O. Let's say this point is O prime, and let's say that the contact point at a given instant, at an arbitrary instant, is C. This is the contact point of this base circle on the horizontal ground. Now the cone is rolling without slipping, and it rolls with a constant angular velocity omega. Okay, and as that happens, you can imagine that this point P is going to go around in a circular path with respect to this circular area at the base, and we want to find the velocity of this point, okay, at an arbitrary instant. And the approach that we will take is to use a rotating coordinate frame. Our coordinate frame is going to be well, you can place the origin of the coordinate frame. It is of secondary importance where you place the origin of the coordinate frame, because the vectors will be the same where you irrespective of where you place it. But let's say that the coordinate frame has capital I as the unit vector in this direction. So I is going to be, and let me explain the rotation. So capital Z hat is the unit vector in the vertical direction, and then the unit vector y hat is the unit vector which is mutually perpendicular to I and Z, and it is pointing into the surface, thereby forming a right-handed coordinate system, right? So you have a I, J, K, this should be I. So I'm just indicating the unit vectors, I, J, K unit vectors. Okay, so this is a triad, as you can see, and essentially we will say that I, J, K forms a rotating triad which turns with the cone about k axis at the angular speed of omega. So this statement tells you how the IJK coordinate frame, or rather the IJK triad, how it turns. So we have a rotating frame which turns with the cone, in the sense that it turns with an angular velocity of omega. So if you, for instance, looked at this cone from the top view, what you would see is the following. You would see, so let me just make a smaller diagram here. If you looked at the cone from the top view at any arbitrary instant, what you would see is something like this. You would see the cone. So now you're looking at it from the top, and your I unit vector would be directed this way, and it will be horizontal. J would be directed this way, and K would be directed out of the page, and the cone is turning with an angular velocity of omega. So this is how the motion is happening. This is how the coordinate frame triad is turning, and the center of the cone is here, and let's say that the point P is somewhere over here, and it is turning with respect to the circle, the circular base. So this is the top view. Top view of the cone as the cone rolls without slipping, right? So one thing that you can see is that Ki, the axis K and the axis I, or the unit vector K and the unit vector I, always remains vertical, right? So that's an observation. Okay, so with this, then we will start solving the problem, and now for we know that when we solve a problem when we use a rotating coordinate frame, then the velocity of a point, when you express it with respect to another point, and you are expressing the whole motion within a rotating frame, then of course we have Vp. If I'm interested in Vp, I can usually when you solve problems like this, you try to express Vp or the velocity of the point with respect to another point, and this other point is chosen where you feel that its velocity can be more easily determined. Okay, so I am going to express the velocity of P in terms of the velocity of O prime. So Vp is Vo prime plus the velocity P with respect to O prime. Okay, this is the basic relative velocity equation. And one thing, if you recall from our previous videos, is that whenever we use a rotating frame, then this relative velocity gets split into two parts. One is the omega cross rho plus the other is rho dot r. So let me just explain. Rho in this case is the vector from O prime to P. Okay, and rho dot r is the velocity of P as observed within the rotating frame. Or in this case, the rotating triad. Okay, and furthermore, omega is the net angular velocity of the rotating triad. So this is how we set up our problem. So we have velocity of P is given by the sum of these three expressions, and we are going to find the velocity by determining each of these vectors. All right, now let us start our discussion with the velocity Vo prime. So first we will find the velocity of O prime, and we can see from the top view that the point O prime is just going around in a circle. Okay, and so its path is circular, and the radius of that circular path is given by this perpendicular distance of O prime from the axis K prime. So if we indicate the or if we denote the axis of the cone by the letter H, then as you can see, that distance is given by H cosine beta. So that that perpendicular distance of O prime to the axis K prime is given by H cosine beta. So in other words, this distance is H cosine beta. Okay, so this is H cosine beta, and the velocity or rather the angular velocity with which the point O prime is going around is this omega. Okay, omega is the angular velocity with which this point O prime is going around in this horizontal circle. So therefore the velocity of the point O prime is going to be the velocity of the point O prime is going to be H cosine beta times omega. And if you think of the direction, the velocity of O prime is going to be tangential to this circle at any point. So basically it is going to be Vo prime is going to be parallel to the rotating J prime axis. So as the axis turns, or as the reference frame turns rather, as the reference frame turns, the velocity VO prime is always going to be directed in the j hat direction. So the unit vector is going to be j, and that's the velocity of v of O prime. All right, so that's the first one. The next item that we need to figure out among all the 4 things that we need to figure out in order to complete the velocity is the angular velocity, and as we have said, omega is the angular velocity of the rotating triad. So what is the angular velocity of this rotating triad? As we have discussed, as the problem states, that the axis of this cone is turning with an angular velocity of omega, and so that omega is about the k axis, so it is going to be omega k. Furthermore, let us figure out what rho is going to be. Okay, as we have given over here, rho is the vector going from O prime to P. Okay, so rho is essentially this vector, and it is directed from O prime towards P. Okay, so it is directed from O prime towards P. Okay, so this vector needs to be resolved a little bit, and let me just try to make a sketch to show how O prime gets resolved. So if we consider this ellipse that is forming, we are using this as a view. The axis of the cone is like this, right? We are just focusing on the circular base of the cone. Now you can translate the ijk, this ijk you can translate to this point, just so that you have just so that it makes finding the components of O prime P a little bit more convenient. So I is in the horizontal, I prime is in the horizontal direction, k prime, or k hat rather, not k prime but k hat is in the vertical direction, and j hat is mutually perpendicular to I and k. Okay, but let's say that it is shown here in this oblique fashion, and let's say that the point P is here, O prime is here, and this is the vector that we are trying to find out, right? And the vector makes an angle phi with respect to the line joining the contact point with the topmost point. Okay, essentially, if you are looking at the circle that forms the base of the cone, then what you are looking at is something like this. So this is O prime, P is here, that's the vector O prime to P. This is, by the way, an inclined circle, right? So this is an ellipse actually, but I'm just drawing it as a circle to give you a sense of the view. Well, if you are looking at it from the front, then it's going to be an ellipse, but if you are looking at it in the direction of the axis of the cone, then it is going to be a circle. and this is the point of contact C, which by the way is here. And the angle phi that we showed is this angle, right? So if you do a little bit of solid geometry here, the vector O prime to P, first of all, it's of length small r, because small r is the length, is the radius of the base of the cone. And if you resolve r along the face, if you resolve O prime P along the face of this circle, then you will have r sine phi to be along the j direction. Okay, and r cosine phi will resolve the O prime P along this inclined line. And by the way, this inclined line is going to be making an angle of beta with respect to the vertical k-axis, because that angle beta comes from the fact that the cone itself has the angle beta, and so this line makes an angle beta with respect to the vertical. Okay, by virtue of the fact that the base circle is tilted by an angle beta. So r cosine phi is going to resolve along this inclined line. So r cosine phi is going to resolve O prime P along this inclined line, and then cosine beta of that is going to resolve it along k hat. Okay, and r cosine phi sine beta with a negative sign is going to resolve it along the I axis, I hat axis. Okay, so that's our vector rho. Okay, so it's a little bit complicated because of the fact that there is a little bit of solid geometry that is involved here, but that's the way we find out this vector rho, okay, in terms of the IJK triad that we have chosen. All right, so now the next step is going to be to look at rho dot r. Rho dot r, as given over here, is the velocity of P as observed within the rotating frame. Okay, so I'm just going to write the expression for rho one more time, is equal to r sine phi j plus r cosine phi cosine beta k minus r cosine phi sine beta I. Okay, and next we will try to determine this rho dot r. Now the rho dot r is, as the as the definition says, it's the velocity of P with respect to O prime as observed in the rotating frame. All right. So I should clarify that this is velocity of p relative to O prime as observed within the rotating frame. Okay, so now when we find the velocity within the rotating frame, what we are essentially saying is that if you are moving with the rotating frame, what is the velocity of p that you would perceive? Okay, so that can be found by taking the derivative. So rho dot r can be found by taking the derivative of rho while assuming that the reference frame is static. So if we want to find the velocity rho dot r, that is the velocity of p with respect to O prime within the rotating frame, we can take this position. This is the position of O prime, or rather p with respect to O prime. So we can take that vector and we can differentiate it. But when we differentiate it, in this differentiation, this is a special differentiation where we do not consider that I, j and k are moving. Okay, when we put that assumption, that basically amounts to finding what the velocity of p would be with respect to O prime within the reference frame, within the rotating frame. Okay, within the rotating frame. If you were to differentiate I, j and k also, that would mean that you are now incorporating the fact that the frame itself is rotating, and that incorporation is actually done in this term, so we don't need to do it again. This part just finds the velocity within the rotating frame. So let's take that derivative. So then we will have rho dot r is equal to r is a constant but phi is changing, so r phi dot cosine phi j, and although j is turning, indeed j is a rotating reference, a rotating a unit vector in a rotating reference frame, but we are not going to differentiate j, so we are not going to have a j dot term here because we are only finding the velocity within the rotating frame. So so that part will not have to be included here, plus r sine phi negative phi dot cosine beta, and beta is the angle of the cone, so that is a constant, it's a parameter. And similarly you would have minus r sine phi negative phi dot sine beta I. Okay, so that's the vector, and now we simplify it. So we have r phi dot cosine phi j minus r phi dot sine phi cosine beta k plus r phi dot sine phi sine beta I. Alright, so now essentially we have all the different components and we can add them up. So then we say that Vp is therefore Vo prime plus omega cross rho plus rho dot r, which is equal to my O prime was h cosine beta omega capital J plus the angular velocity is omega k cross rho. Rho is let me just double check here. Is r sine phi j plus r cosine phi cosine beta k minus r cosine phi sine beta I. Okay, and to that we add this velocity in the rotating frame, so that's r phi dot, and I'm just going to put everything else in brackets, so cosine phi j minus sine phi cosine beta k plus sine phi sine beta I, right? So now it's a matter of algebra. We need to do this cross product. So I prefer to do this cross products just term by term. I will use k cross j. So we have this unit vector triad, so I, j and k, and this is the way the triad works. I cross j is k, j cross k is I, and k cross I is j. So k cross j is going to be minus I, so we will have a minus I term here. So I'm going to combine that with this minus I term. K cross k is going to be 0, k cross I is going to give me a j, so there will be two I terms. So let me put them together. So it's going to be negative omega r sine phi plus r phi dot sine phi sine beta I plus, let me put the j terms together, so h cosine beta omega. K cross I is going to give me a j, so k cross I is a j, so we'll have minus r omega cosine phi sine beta, and that's going to be a j term. However, k cross I gives me j, capital positive j, so then this negative sign remains, and then I will have a j term from here, so plus r phi dot cosine phi j. Okay, so that's my j term, and there is just one k term, and that is this guy. So we have r phi dot sine phi cosine beta, and this is going to be a negative k, so I'm going to just negative sign here. Just checking to make sure we have the right expression. Yeah, so the problem is not done at this point, and that is because I want to bring your attention to the fact that when the cone rolls without slipping on this horizontal surface as seen from the top here, the rate at which the cone, the center of this cone or O prime, the rate at which it is going around in a circle also determines the rate at which the point P is rotating about the point O prime. Because they are all connected, it is just one motion. It's just a 1 degree of freedom motion. As the cone rolls, there is going to be a definite angular speed with which P goes around O prime. So what that means is that phi dot, so this is phi, and phi dot has got a direct relation with omega, and that needs to be found out. So the way to find that is the following. So let me just use a different page. So there are multiple ways to finding out what that rate of angular, this rate of rotation is. A rather simple way to find it out is by considering, or by observing that the point C, by virtue of the cone rolling without slipping, the point C does not have any velocity. So the velocity of the point C is 0. So if we can split the motion of this cone into two types, one is the fact that the cone is just spinning about its axis, O prime, and the other is it's not spinning, but O prime is just going in a circle. So there are two motions. If we can consider the motion of the cone as composed of two motions, one is O prime going around O in a circle, just as shown over here. That is one motion. And the second motion is the cone is just spinning. Okay? And if we take these two motions separately, then we can impose the fact that the point C must have a 0 velocity for rolling without slipping. And when we impose it, then we get the velocity, an expression for phi dot. So that's an easy way. There is also a formal way to find it, and we will show that in following videos. But for now, we are going to just consider. So consider cone just spins about O prime. Okay, if that was the case, then VC, and I'm not this is not a formal calculation. I'm just demonstrating a way to relate these velocities quickly without doing too many calculations. I will show a formal calculation of this phi dot in following video, but now we just considered the cone to be spinning about the O prime axis, and if that was the case, then what would have been the velocity of VC? It would have been phi dot r. Think about it. If the cone was simply spinning about the O prime axis, and for the moment forget that there is a ground, just spinning about the O prime axis, and the O prime axis is fixed. Okay, in that case, the velocity of C would have been phi dot r, and it would have been going out of the page, right? So that is one aspect of the motion, of the overall motion of the cone. Next, consider the cone to be turning without spinning about its axis. Okay, about K. Okay, so indeed, if you consider the OO prime, it is just turning about the k-axis. So if that was the case and the spinning was not there, then what would have been VC? Then VC would have been this distance times omega. And what is this distance? This distance, if this distance is h and if this is r, and this is a regular right-angled cone, then this distance from O to C is going to be square root h squared over plus r squared. So square root h squared plus r squared times omega. So that would have been the velocity of C, and it would have been, in this case, it would have been pointing inwards, and in this case, this would have been pointing outwards. So I'm putting this circle with a dot to show that this spinning causes C to have a velocity going outwards perpendicular to the page, and this velocity of the cone turning causes C to have a velocity into the surface of the page. And so we know, however, C is at zero velocity, right? Because the cone is rolling without slipping. In fact, for that matter, any point on this line OC, which forms the line of contact between the cone and the ground, is instantaneously at rest, because that's the definition of rolling without slipping. The ground has no velocity, so therefore the contact line must have zero velocity as well. So C is at zero velocity, so therefore phi dot r must be equal to omega times square root h squared plus r squared. Okay, and so we have phi dot is indeed related to this angular velocity omega, and it is omega times square root h squared plus r squared divided by r. Now if you consider this right triangle formed by h, r with an angle beta, then what is r divided by the square root h squared plus r squared? Well, that is sine beta, so you have omega divided by sine beta. And so here you have an expression then that phi dot is omega divided by sine beta. Okay, and this is a very important expression because this relates how the rotation of the spinning of the cone is related to the turning of the cone. This relation being enforced by the fact that the cone is rolling without slipping. Okay, so with this as our result, phi dot equals omega divided by sine beta, we now will go back to our velocity expression and substitute this. So then in the I direction we will have minus omega r sine phi plus r times phi dot sine beta is going to be omega, so phi dot sine beta is omega times sine phi I. In fact, that basically says that the I component is cancelling for the velocity of p. P does not have an I component. In the j direction we have h cosine beta omega minus r omega cosine phi sine beta, and phi dot is omega divided by sine beta, so plus r omega cosine phi divided by sine beta. And this is in the j direction. Minus r omega over sine beta sine phi cosine beta k. right? So that's the expression for the velocity. You can also make the observation based on this triangle here. You can make the observation that r divided by h is tangent of beta. Okay, so here you have r divided by h is equal to tangent of beta, which means that r cosine beta is equal to h sine beta. Okay, so at this point you can express everything in terms of r, or you can express everything in terms of beta. So in terms of r or in terms of h. So for instance, I can go and replace all these h variables by r cosine beta divided by sine beta, so that the whole solution is in terms of r and omega and phi and beta. Or I could express everything, or I could express r in terms of h, and then the solution would be in terms of h and beta and phi and omega. So that's our solution. And let me just check if we have the right answer, which I see is indeed, yeah, so we do have the right answer here. So that's the end of this video. In the next video, what I'll do is I will try to do two things. One is solve this same problem using a different set of rotating unit vectors. So I'll take a different triad. It's also going to be a rotating triad, but it's going to be oriented differently, and we'll solve it this way, using the same way but with different rotating frame, number one. And number two is I will show a formal way of finding out the relation between phi dot and omega. Today we kind of took a visual approach to find out what phi dot is, but there is a formal way that you can apply as well. It becomes a little bit more lengthier because it involves some more calculations, but I'll show that in the next video. So that's it for this video, and we will discuss these techniques more. Thank you.